Hey guys, and welcome to another video in this computer vision tutorial and OpenCV tutorial. In this video we're going to talk about noise and smoothing on images. And let's go to the first slide here, where first of all we're going to talk about noise in images and how they affect the image, and also then we go over some different kind of solutions of how to reduce the noise and smooth out the noise in images as well. So noise, almost every image is affected by some kind of noise, and it degrades the image. So like the quality or resolution, it gets worsened, and it can mess up some of our operations and stuff like that if we don't try to do some pre-processing on the images, or smoothing, or doing something with the noise to some kind of degrade the noise in the image. And as I just wrote here, it can cause problems to the processing on the images that we're doing. But what are some of the things that can cause noise in an image? And one of the most often ones is measurement noise. So it can be when we're measuring different types, like when we're measuring the lights coming into through our lens in our camera. Then there's some kind of measurement noise that can be caused to give a noisy image. And we often denote it is in this signal to noise ratio, where we have some kind of signal that is affected by a noise. And if we go down here to the figure down here, we can see that we have our received signal here, which is the green line, and then we have the power up here on the y-axis and time on the x-axis. So this is a signal that we receive through time. And then we have some noise coming in as well, together with our received signal, and that noise can be caused by many different things. And we try to reduce this noise that comes in here together with our signal. So the distance here, or the difference between our received signal and the noise that comes into our image, is called the signal to noise ratio, and it's denoted in decibel. So we're trying to get a signal to noise ratio, which is a maximum value. So the signal to noise ratio should not be very tight, because then our noise is very close to the signal, and then it's really hard to smoothen out or fill the noise away to get a more clear and a quality image. So one of the most noisy one of the elements that can cause noise on images is the salt and pepper noise, which is as we can see down here on the images here, which is kind of an impulse noise, and it is caused by defects in camera pixels. So let's say here we have a camera, this is just for demonstration. Often there won't be so many salt and pepper noise on an image, but for demonstration it's very good where we have an image here where there are some defect pixels in our camera, and then our image will look like this on the right here compared to what it should have looked like on the left here. And salt and pepper noise is it's an impulse noise, so it's either a maximum or a minimum value. So it's either 0 or 255. So it's not really good to have salt and pepper noise on our image, because when we're doing some operations and calculations on our images, and we suddenly see a pixel going from, let's say, 60 to 255, and when we're trying to do some calculations on that, and when we're running a slider or a kernel filter over our image, that will cause a lot of problems if we have this salt and pepper noise. We also have something called Gaussian noise in images, which is most of the noise that comes into our image is Gaussian noise, and it's also it does look like real noise to an image, and it's kind of a distribution of the distribution of the noise is Gaussian. So we talk about this Gaussian graph here, where we have the mean values and standard deviations in our noise. So here we can see that our noise, it's not really, we can still see what's happening in the picture, but the noise is distributed over the image, so it just gets a bit more blurry and stuff like that. But it doesn't really destroy the image, but we can still do some pre-processing with the image to try to smoothen this Gaussian noise more out, so it'll be a better quality picture and it won't affect that much our 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 image processing. So when we have noise on our picture, we need to like smoothen out that noise, or like in some kind of way try to reduce the noise in our image, so our processing and calculation operations on our images are more reliable, because we need like the same pictures all the time when we're trying to like, if we try to do the same thing over and over again and our images are different, like there might be some differences as well in the calculations and then in the result as well. So smoothing is to remove or reduce the noise on images, and we have some different kind of smoothing where we have like the linear smoothing transformation and non-linear transformations. So like the linear smoothing transformations are like image averaging. So let's say we have several images, then we're just taking like the average of all those images. So if there's noise on some of the images, then it will like be reduced because we're taking the average of, let's say, like 10 images and there were noise on 2 of the images. Then we will average out that noise on the image. And you also have like something like a local and Gaussian smoothing, which I'm going to show you some examples on later on, and also in code, where we're going to take in an image that is taken in an image, and then we're going to blur it and smooth it out again with this Gaussian smoothing transformation here. We also have some non-linear transformations where we have, like, for example, a rotating mask rotating around in the picture and trying to smooth out the image, or a median filter, which I'm also going to show a code example on, and then a practical example where we take an image and try to smoothen it out. So when we're averaging the images and to try to smooth it out, we can see here that we often do it with, like, for example, when we're taking pictures or doing some analysis in the space or galaxy, because the quality of the images are very they're not really good, and because they're so long, such a long distance, and we will get a lot of noise on those images. So let's say here to the left here we have a single image that is taken, and we can see there's a lot of noise around here on the image. But then we can take here in this case we're taking 21 images and then fold stacking it on each other. So we're doing an image averaging on all those 21 pictures. So we're taking the average of all those 21 pictures, and then we're combining them all to one picture, and we can see we have reduced or actually removed a lot of the noise around in the picture here. So this is a kind of good linear transformation to try to smooth out an image if we have some noise on it. We also have the median filter, which is a non-linear filter, and I'm going to show you an example of it. So the median filter uses the median value. So let's say here we have some pixels value here for our pixels, and then when we're taking the median, we're just taking the middle element here on our pixel list. So in this case here it will be 23, which is the median. And we often use the median because if we, for example, just took the average of our image, which is just a linear transformation, then if we had some, let's say we had some salt and pepper noise on one image, then we'll get some high values like 250. And if we took the average, it will impact the image a lot if there were some spikes or high values that isn't really in the picture and it's just clearly noise to the image. And then if we took the average of those values here, we'll get 74, and it is not really the average because we had such a huge spike up here. So we often use just the median value, and it's more reliable and better if we're just getting some noise on our image once in a while, or have some defect pixels on our camera. So the median filter here is not really affected by noise, and it doesn't blur edges much. I'm going to show you an example as well where some of the other filters they blur out edges in the image. And if we want to do some edge detection or some object detection or something like that, then we don't really want the edges to blur out. And it also, the median filter, it also damages thin lines and sharp corners. So let's say we have some house and we have some thin lines in that house, or sharp corners in some arbitrary way, then it will like damage those lines and they won't really be clear. We can see here we can use this median blur here if we want to like blur our image with this median filter here, and we can give it the image we want to blur, and then the output image here we want to blur, and then give it some kernel filter here, which will look like this if we give it like 5. So we also have some smoothing examples here where they're using some of the filters we have talked about in the previous slides. So the test is just over here, like it's the original picture that we load in, and we can see there's like a lot of noise in the sky and also on the buildings, but the edges are still pretty clear and stuff like that. And then we can use what's called like a box filter or an average filter, where we're just averaging out all the values in the picture, and we can see like it's actually it gets more blurry here, but we reduce like some of the noise in the sky and also in the buildings, but the edges they get more blurred out, and it's not really that clear compared to like just the original picture, like all the lines and objects in the image. Then we also talked about like the Gaussian blur, where we try to like find like a median or like a standard deviation, like all the values have to be inside like some defined standard deviation. And then we can see like we reduce the noise here in the sky and also in the buildings, but we still get a bit more clear edges compared to like just the average filter. And then we have the rotating mask, which we just talked about, which will blur out like lines, and I'll just go back here, like it will damage like thin lines and sharp corners, and it doesn't like blur edges much. So we can see here that like some of the sharp lines here, they don't really like, they get really damaged here and also like up here. So the edges on the image, it gets really damaged compared to some of the other filters, but we still reduce some of the noise. But this is probably not like the optimal filter to use in this example here. And then we have the last example here with the median filter that we'll be using, which is like probably the most optimal filter to use in this situation here. It kind of looked like the average filter here as well, but it's not really like that blurry here in the buildings, and the noise here in the sky and on the buildings, like they're reduced, and we still have sharp edges that we can detect. So this median filter here is actually pretty good for this example here, and it was just to show you some different kind of examples. And when you have a problem and you try to solve that problem, like you probably need to use a different kind of filter to see what gives the best result, because it's really like task and problem dependent. And when you get used to using more of them, and when you tried a lot of filters, like you know in which kind of situation like one filter it could be better than another filter. And then in the end here, I just have some like OpenCV hints for you guys, where when we're using OpenCV, our images is just created as matrices, and this example here is just like how to create a matrix in OpenCV, where we have this matrix object from the OpenCV class, and then we can give them like the rows and columns we want to, and then like the data type we want our values in our matrix to be in, and then we create our matrix here. As we just do with images, but like we can also like have mat and then load an image in, and then that will be stored, like then our image will be stored in a matrix. And then we can also see like down here that here we have like the assignment operator. When if we try to do like b equals a here, we will not get a copy of our matrix in OpenCV. Like if we do like, let's say here we have like b equals a, and we do some operations on b, that will also affect a, because we're just like pointing to the same memory location like pointing to the same memory location, and then we're doing operations on the data that is in that memory allocation. So if we want to copy our image and we want to like double store the new matrix in our memory, so we have like a copy of the image, we have to call this function like a copy to b, and then we will create like a copy and have the double memory. So, or also like this, we can assign like b equals to a, and then clone the a matrix and store it in b, and then it will like create a new block of memory that we can now do operations on b without it affecting the a matrix. So here is just like how we initialize our matrices and how we do like different kind of operations on them. So here we can like, for example, set up some different kind of initializations, and we can use like, we can also like use our matrices like in some MATLAB style array where we can do some operations on them. Like for example, here we can create a double precision identity matrix and add it to M. So we can do like these multiply and plus operations on matrices and images as well in OpenCV, which is really useful, and also when we're going to apply filters and stuff like that, because it is like when we're like doing operations on images, it's mostly just linear algebra and matrix operations. When we try to like extract some information or do some filtering or smoothing on our images, and then how we can access an element in our picture. Let's say we have like, for example, a picture that we want to access a specific individual element or a pixel or some like pixel array inside of that image. We can do it with here we can, for example, say here we have like this add operation, like, or add function here, and then we can say like add this image M here, and we just like multiply or like add, we just add one to that, like each pixel in our image. And then we can also like compute sum of positive matrix elements and stuff like that, where we just go through all like the picture pixels and stuff like that in our image, and also like compute the sum of positive matrix elements and other stuff like that. Like here we just have another operation where we use iterators, where we're just running through our all of our elements in the matrix. So it can either be like a matrix that we set up ourselves or images, and you can go more in depth with these code examples or look them up in documentation if you want to, or else we'll just jump into the code and I'll show you some examples of like how to use some of these smoothing and blurring on images. So we're now jumped into Visual Studio here, and I'm going to show you some different kind of examples with the blurring and smoothing codes and concepts that we just talked about in the slides. So first of all, we're just going to include the basic like the IO stream and the OpenCV library, and then we're calculating some max values here that we're going to use later. But first of all, we're just going to give it the image paths of the images that we want to load in and do some kind of operations on. And I just specified here the path where I have stored the images that we're going to use. I've uploaded the code and images to the GitHub that I'll link down in the description, so you can go check that out and try to do it yourself if you want to. But first, we're creating this matrix object here, which is called image, and then we're just reading in the image from one of the paths that we defined up here, and we're reading it in as I call it image. And then first of all, we're just going to resize the image so we get a 500 by 500 image that we can do some operations on. And first of all, we just check if the image is empty, the image we load in, because if we can't load in the image, it will just return 1 and terminate the program and just tell us like it could not read the image, and then we can go debug that, and if it doesn't run this code, we know that the image is loaded in successfully. And if we start with blurring out the images, we'll just go down here and create 2 new images here, or matrices, where we have this medium blur image and the Gaussian blur. So we're going to do an example where we first blur out the image with this medium blur, and then we have an example with the Gaussian blur down here, and we just pass in the image that we want to blur out, and then our the output image that we want to store the blurred image in, and then the size of the kernel, like or the filter that we want to run over our on our image. So if we print this out, we'll just print it out with this imshow command here, and then we will print out the original image and the medium blur image and the Gaussian blurred image. So if we hit run program here, we can see here we have the original picture here, which is like not done on the operations on, and then we can then to the right here we have the Gaussian blur, which is like still kind of looks like the same. We can't really see that many differences like between these two images here, because we're using Gaussian blurred, so it's like all the data has to like be inside of the, like a standard deviation and like the mean values. But if we use the median blur out here, and we take the median values as we talked about in the slides, we can see like the image gets like really blurred, and like some of the objects, they are not really like the lines in on the objects are not really that clear anymore. So this could be like, for example, an image that we want to do some operations on, or try to like filter it afterwards to like reduce some of the noise or blur like the blurred out. And we can also, like, if we had some more noise on this image here, we could have reduced some of that noise or removed that noise with some of these filters. And we can see like over here we have like some of the noise is not really that good quality picture here, but here is like it's more the picture is more smooth, and we have smoothed out some of the objects, so there's not really like that much noise, and the color is also like more clear. So actually this is a pretty good smoothed out picture compared to like the original one. And when we're doing operations in computer vision, like we just want the images that are optimal for algorithms and not really like optimal for our eyes. So we just prefer like having an image that is good for doing operations and for our algorithms. So we just close this out, and we have now like smoothened out or like blurred some images. And I'm also going to show you some examples of how we can, for example, if we had a picture, an image, and we want to extract some information from that image. Let's say in this case here we have some spoons or hats that we want to like detect in that picture, and we're going to apply some threshold for that image. So let's say we want to threshold or extract the red like the red color from an image and want to detect spoons or hats in this case. So I'm just going to comment this in again so we can see what I mean. And we do this up here where we first convert like our color from our image to to the HSV color model. So we're going to do operations on the HSV instead of the BGR values, which is like what we're used to. And then we set this max value up here, which is just like a standard setup for the HSV color model. And then we set like some lower bound, which is just like we just try to like do trial and error with these values here to try to hit like the red value that we want to extract from our image. Or if you want to extract some other color or information from an image, like you can just play around with this lower bound here. And then we use a function down here which is called inRange, which is going to like do this detection of objects based on the HSV range value that we defined up here. And then we can extract information from our pictures with using this threshold value that we set. So it takes some image that we want to extract information on, and then it just takes like the image, like the threshold values that we want to like have. So it can either be like a 1 or 0. So if it's a 1, then it's because like these values, like the values in the pixels are inside the range that we have defined here. And if it's not, it will just be a black pixel. And then the last parameter here is just the image that we want to like store our output from this function in. So if we just hit the run button here, it will print out the images, and we can see like in this example here, we have the original picture here to the left, and then we convert it to the HSV color model. So it will like look kind of funny to us, but like for the computer, it's easier to extract information in the image here when we convert it to the HSV. And we can see over here to the right, we did the threshold on the image, so we try to extract the red pixels here from the original image, and we can see that we actually like extracted it pretty good. And we have the hat here with the red values, and we also had some red hat over here which is detected here, and we have a hat here, and it's here, and we also have some like small hats which is like pretty blurred out on the original image, but we still detected it over here. And we can also actually see like the red thing here on the computer, it also detected it down here. And then you can just go in and optimize those values here for the lower bound to get it more precise and optimal. But I also have another example here, like the last example I want to show you, where it just like it's more clear that it really like just extract those values from the image that we want. So here, if we run it, we have our original picture over here where we have a red hat, and then we have some background with some gray and white, and we have some text down here with the red hat, and then we can convert it to the HSV color model here. And then we can see like we get a pretty good threshold image over here where we actually only detect the hat and like all the edges, they're really good detected, and even the like the black line here on the head is also pretty good. So like this is a really good extraction of the original image here, and we can use this like for some kind of object detection in images where we just extract the values or the like the information we want in an image, because we don't really want all the background or noise and stuff like that from our image. We just want the only thing we want is the head in this case, and we just extract out everything else from that image. So it can be really useful for like object detection and stuff like that inside of OpenCV and just in computer vision in general. So yeah, that's pretty much it for this video, and we've been over like some of the like noise and how we can smooth out that noise or reduce the noise on images if we get some noise from our camera, which is like often the case. Like it's not really that often, at least not with like with low quality cameras, that we get an image that is just perfect from the beginning. So we have to do some operations like or pre-processing on that image before we can do good and optimal operations on that image. So yeah, thanks for watching this video, guys, and remember to hit the subscribe button and bell notification on the videos, and also like this video so you can show the YouTube algorithm that you like this content and you want more of it in the future. So I'm currently also doing this artificial intelligence and algorithms and data structures tutorials. So if you're interested in one of those, like I'll link to one of them up here, and you can go check them out if you want to, or else I'll just see you in the next video, guys. Bye for now.